Hi, let's talk about finding the domain of a function. So recall, the domain of a function f of x is a set of all the x values for that function. To be more specific, the domain is a set of all the x values that can be plugged in that will result in f of x being a real number. So I've got a handful of examples here that I just want to look at and sort of tell the answer to. This one right here, first example, the domain is going to be all reals. Reason is that's just a line. 2x plus 4, we could graph it pretty easily. It's going to look kind of like that. Its domain, it's going to take on everything. Basically, there's nothing to go wrong there. This next one, 3x to the fourth plus 6x squared minus 9x plus 1, that domain is also all reals. You can plug in any value you want for x, and you're not going to have any problems. These other two are a little more interesting, though. For g of x equals the square root of x, we know that if you take the square root of a number, if you want to get a real value out of it, we know that x has to be at least 0. Can't be negative. So for the domain of this, we would say it's everything from 0 to infinity. And on this one over here, 2 plus 4x over x minus 5. The only number that would cause a problem if we plugged in there is 5. So this we'd say the domain is all reals except 5. Or if we wanted to write that using interval notation, we could say that's everything from negative infinity up to 5, but not including 5. Together with everything from 5 to infinity. So either one of these is a perfectly good way to write this. I would probably just go with all reals except 5 because it's, I don't know, it's shorter or, well, whatever. Go with either one. All right, so these examples kind of showed us something. The only thing we have to worry about for now when we're trying to find the domain of some function is square roots, or actually any even root. The value inside has to be non-negative, and for denominators, the value can't be 0. So let's find the domain of these two guys here. Up here, it was kind of easy on this previous example because we're just looking at the square root of x, and so we said x has to be non-negative. Down here, what we need, though, is, for this one, we need 3x plus 7 to be 0 or greater. So what you do with this is you solve an inequality. You set 3x plus 7, and you say that has to be greater than or equal to 0. So then we'll just move the 7 over, then divide by 3. We get x has to be greater than or equal to negative 7/3. Now, how would I write that in interval notation? Well, honestly, I would do this. I'm going to write my real number line. I'm going to put negative 7/3 on it. And let's see, we can include that, and we also want to include anything that is, notice this says x is greater than or equal to. So we want to include everything above it. So x could be any of those numbers there. So my domain here is going to be everything from negative 7/3 to infinity, including 7/3. All right, this one over here, we're going to do it the same way. This is a fourth root, but it doesn't matter. As long as it's an even root, the thing underneath has to be at least 0. So I'm going to set 5x minus 9 has to be greater than or equal to 0. So 5x has to be at least 9. X has to be at least 9/5. So I could draw my number line again, but I'm not going to this time. That means x has to be 9/5 or greater. So that's my domain. Now you might say even roots. What about odd roots? Odd roots are fine. You can take the cube root of a negative number or the fifth root of a negative number. It doesn't matter. It's only the even roots you have to watch out for. All right, so let's do this example. Find the domain of this thing. All right, there are no square roots in it, so the only thing we need to do is we need to figure out what makes the denominator 0 and exclude those numbers. So I'm going to factor this. When I factor the bottom, x plus 3 and x plus 7 will do it. And I could factor the top too, but there's no real need to. I'm going to do it anyway. Let's see, that'll factor into x plus 7 and x minus 1. Yeah. So what we need to do is we need to throw out the two values that make the denominator 0. Throw out x equals 3, or negative 3, and negative 7. So our domain here is going to be all reals except negative 7 and negative 3. Or if you want to write this as an interval notation, you could say everything from negative infinity to infinity. We have to throw out negative 7 and negative 3. So that's going to be everything there. That's thicker than I meant for it to be, but that doesn't matter. All right, so we get an interval for each one of the thick places here. Everything from minus infinity to negative 7. Everything from negative 7 to negative 3. And everything from negative 3 to infinity. So either one of those is a perfectly valid way to write that domain out. Now, it's important that you throw out the negative 7. If you come back up here and look at it, you might say, well, could I cancel these two guys? Well, if you do that, it actually changes what the function is, because this function is defined on everything except negative 7 and negative 3. If we were to graph this, let's look at it on Desmos. If I graph this function, y equals, let's see, x squared plus 6x minus 7, all that over x squared plus 10x plus 21. If you look at this graph, you'll notice two things going on. Over here at, see, it's kind of difficult to point at it, but if you look over here at x equals negative 3, let me put that in. If you look at that line there, the function's not defined there. That's an asymptote. So it's undefined there. It's also undefined at negative 7. Now, we've got to zoom in, and if you just look at the function here at negative 7, it looks like it's defined, but it's not. If I start tracing along the function, when I get up here to 7, let me see if I can stop immediately on there. It says negative 7 undefined. So that's not included in this function. Now, if we were to graph, or if we looked at the function that we'd get by eliminating this, we get x minus 1 over x plus 3. That function would be almost identical to this one. The only difference would be the only difference would be that function would be defined on the point negative 7. All right, let's look at a couple more. Okay, find the domain of this function. Well, what we'd have to do here is just throw out anything that makes this 0. So we throw out the solutions to x squared plus 5 equals 0. Well, that doesn't have any real solutions. and we're only interested in real numbers right now. So this has no real solutions, so therefore there's nothing to throw away. So the domain here is going to be all reals. And we could graph this if we wanted to, but I'm not going to, because there's nothing exciting that's going to happen. There's not going to be anywhere where it's undefined. All right, let's look at these two functions. Notice these are closely related. F of x is 10 minus the square root of 10 minus 8x. The domain of this is going to be, let's see, we'd set 10 minus 8x to be greater than or equal to 0. Now I'm going to move my 8x over to the other side. So x has to be greater than, or x is less than or equal to 10 over 8. So x is less than or equal to, let's see, 10 over 8, that's 5 over 4. So that's everything from, let's see, 5 over 4. X has to be smaller than that, so that's all the stuff down here. And it's or equal. So our domain here is minus 5/4. Oh, wait, that's the top end, so that's my upper end point. My lower end point of the domain is negative infinity. Okay, so what about this other function? Notice it's got a square root, but the square root is in the denominator. So we need two things for this. We need 10 minus 8x to be greater than or equal to 0. But because this is in the denominator, we need 10 minus 8x. It's square root. We need the denominator to not be 0. So what I would do here is, the answer to this winds up being minus infinity to negative 5/4, but you can't include negative 5/4 because negative 5/4 makes the entire denominator 0. Let's look at another example. Find the domain of this guy. All right. So actually, before we do that, let's go back and look at this. Notice the difference in dealing with square roots and with denominators. With the square roots, you decide what to keep. With the denominators, you decide what to throw away. So when you've got both of them here, you have to take both of those things into account. Now this one, I can factor the bottom into, let's see, 2 and 7. If I make both of them negative, yeah. So x minus 2 and x minus 7. So this tells us that I have to throw away 2 and 7. And the numerator tells me that I have to have x plus 5. I don't need the square root. X plus 5 has to be at least 0. So this tells me that x has to be at least negative 5. So I'm going to draw this all on my number line. Now, don't put anything on the number line that you don't need. The only numbers I'm going to put on here are 2, 7, and negative 5. So here's negative 5, here's 2, and here's 7. Okay, x has to be greater than or equal to this, but it can't be equal to 2 or 7. So 2 and 7 both are going to have open circles there. And now, let's see, this says x has to be greater than or equal to negative 5. So it's going to be here, going up to here, here, and here. So my domain is going to have three parts to it. Negative 5 to 2, together with 2 to 7, together with 7 to infinity. And that's probably the most economical way to write that out, is to just give it as a 3 intervals union together. All right. The last sort of combination here is what happens if you've got two square roots together. Well, this one right here says that x minus 3 has to be greater than or equal to 0. And this says that 5 minus x has to be greater than or equal to 0. So this says x has to be at least 3. And, let's see, if I move the 5 over, I get minus x is at least negative 5. If I divide both of these by negative 1, remember whenever you multiply or divide a inequality by a negative number, you have to reverse the inequality. So this says x has to be greater than 3, and x has to be less than or equal to 5. I left the equal to off over there when I mentioned it. So that's everything from 3 to 5. I'm going to do this in 2 steps. I'm going to put 3 and 5 on both of these number lines. So x is greater than or equal to 3. That's going to be this one. So it has to be 3 or bigger. And x is less than or equal to 5. That says it has to be 5 or smaller. The only values of x that satisfy both of these are the ones that are shaded on both of these number lines. So if I take these and put them together, technically I'm taking the intersection of these two things, but I'm having to take the points that are shaded on both. So that's going to be everything from 3 to 5. All right, let's do one more example. On this one, again, this says 4 minus 3x has to be at least 0. This says x plus 6 has to be at least 0. So if I rearrange this, negative 3x is at least negative 4. So x is less than or equal to 4/3. This says x is greater than or equal to negative 6. So this right here, x is less than or equal to 4/3. Let's put 4/3 and negative 6 on both of these. So if x is less than or equal to less than or equal to 4/3, that's going to be here or back. And x is greater than or equal to negative 6, that's going to be here forward. The only stuff that's common to both of those is the stuff from negative 6 up to 4/3. And so that's our domain. And that's the end.